for this afternoon is by Dmitry Itsykson from Ben-Gurion University of Negev, talking about read-once branching programs as proof lines.
Thank you for introduction. This will be maybe not very technically hard, but overview talk. And, I will talk. No, this is a talk about proof complexity. And for simplicity, I will talk only about mainly about semantic proof system. Consider we have an unsatisfiable CNF formula, and we want to show that it is unsatisfiable. The notion of semantic proof system is based on the notion of proof line. For our case, proof line is just a Boolean predicate that is represented somehow. For example, for resolution, proof lines are clauses. For cutting planes, proof lines are linear inequalities with integer coefficients over Boolean variables. If we consider inequalities of degree k, we have a short k proof system. If we consider disjunction of linear equalities over the field F2, when we get resolution over parities. In semantic proof system, we have generally only one rule. From two proof lines, we can infer any proof line, what we like, if there is semantic implication. And refutation of a formula is a sequence of proof lines such that the last proof lines is equivalent to constant fold function. And every other proof lines either represent of clause of the function of the formula they are refuted or obtained by semantic application rule. And two parameters, length and also size of semantic refutations. For some, in some cases, semantic proof system is not necessarily the real proof system in Kuprichal sense, because it's not necessarily easy to verify semantic rules. For example, for resolution, it is easy to verify. Even for cutting planes, if we consider semantic cutting planes, it is NP hard in general case. For THK also NP hard, but for resolution over parity, it can be done in polynomial time. Okay. The question that I'm interested in is how to prove lower bound just looking on the type of the proof lines. No, there is a observation that if proof lines are too strong, then we can't prove any lower bounds. For example, if we choose CNF formulas as proof lines, then every unsatisfiable CNF has a short contradiction. We just compute end of all clauses. It will be a CNF formula, and this is semantic refutation. The second example, for example, semantic polynomial calculus is also too strong system. Consider, for example, over reals and free CNF formula. We can refute it as follows. We can just consider sum of all polynomials representing clauses and sum of square of Boolean axioms, and these two polynomials requires we will get a contradiction. Okay. Some other result, Krajcik noticed that if proof lines have small deterministic communication complexity, for example, in the model of two participants, that some variables are known for one participant, some variable to other, then in this semantic proof system, click coloring is hard formula, and for example, it gives lower bound for resolution and for cutting planes with small coefficient, with unary coefficient. It can be extended, but it's not so important. If proof lines can be computed by randomized communication, then, for example, lifted Satan formulas are hard for tree-like refutation. Okay. no, the first observation was that if prooflines are too strong, and what is from our other side? Consider, for example, semantic refutation of decision trees. Every proofline is just a decision tree. No, not very deep observation that the resulting proof system is polynomial equivalent to resolution. Let's understand why. No, this is the one semantic step. And it is easy to show that CNF representation of conclusion can be derived from CNF representation of premises in resolution. To see this, every decision tree, how to construct a CNF, we just consider zero leaves and consider clauses that are refuted in these zero leaves. And consider, for example, one zero leaf and clause corresponding to it, and write this path separately, and in standard leaf we hang the first decision tree. After it we delete non-consistent parts, and here it is still possible that here we have 0, and here it's possible that we have 1, and for all ones we hang the second decision tree. And here I claim that it is also possible that there are some ones, but all of them belongs to inconsistent parts. If we delete all inconsistent parts, we will give something like this, and this is just a decision tree. And in this point, the clause, what we consider, is refuted. So this is tree-like refutation of this clause from the clause. And the size of this refutation is polynomially connected with the size of these decision trees. For example, the same also holds if we consider semantic calculus of parity decision tree, when we will get resolution over parities by the same reasoning. Okay. For decision tree, we have very small, simple proof system that for it we have lower bound. But if we consider instead of decision tree, for example, advanced branching program, and this reasoning is not work because each leaf will correspond to many clauses, and we will not get polynomial size resolution refutation. Let's consider. No, let's define the branching program. What advanced branching program? This, for our goal, this is branching program is a way to represent a Boolean function. It's represented by direct acyclic graph. Every vertex is labeled by variable, and two edges outgoing labeled by 0, labeled by 1, and we have two sinks, 0 sink and 1 sink, and to compute the value we go from the source according to the value of variables, and finally onto the sink. That is the value of the function. The one very important partial case of advanced branching program that usually used in practice and software hardware verification is ordered binary diagram. It's a partial case of advanced branching program. Then all variables on all paths appears in the same order. There are one order of variables, and on all paths they cannot appear on another. Why it is important? Because first of all, there are small OBDD representation of many important functions. For example, clauses, parities. For example, this function is parity, and also linear inequalities with small coefficients can be represented by small OBDD. And what is more important, the binary operation for OBDDs, if two OBDD have the same order, can be performed very efficiently in linear time. actually. No, these properties are used for upper bounds. For lower bounds is also will be necessarily form property of OBDD for us, that if we partition variables to two parts that agree with the order, then the communication complexity of computing OBDD is logarithmic of its size, because first of all, first participant go from the source by his variables, and after it he just send the number of vertex, and the second participant the computed result. Okay, and I will discuss in this talk the semantic proof system where read-once branching programs are proof lines. But we start with OBDD proofs. The proof system was defined by Zarias, Kalaitis, and Vardin. No, formally derivation, we choose a variable order of variables for all OBDDs, and we define the following rules. First rule is conjunction rule. For two OBDD, we can infer their conjunctions. The second rule is weakening rule. We can derive any OBDD that semantically implied from the OBDD. And in that paper, they also define projection rule. That is, in fact, a partial case of weakening rule, that for OBDD, we can derive OBDD exists xd, the x is some variable. Why it is more interesting? Because it looks more practical, because weakening rule, there are a lot of ways how to weaken, but not too many rules how to apply projection rule at most number of variables. Okay, no, the goal here is to derive a constant false OBDD using these rules. If we consider only first rule, we will get just semantic proof system with one restriction, that all OBDDs have the same order. But this restriction looks maybe rather artificial, and it is possible to add the reordering rule that we can just derive the same function but written in the other order. All these rules can be efficiently verified using the properties of OBDD. And there are a lot of proof systems defined by this definition. We can use the different set of rules, and we put them in the brackets. And consider some partial case of them. For example, we have only conjunction and projection rule. This proof system is rather interesting. For example, it can solve a system of linear equations, unsatisfiable nunc, I can refute, because if we take two linear equations and consider conjunction and projection of the common variable, we will get just the sum of this equation. And also, this proof system simulates resolution, because resolution rule is also just conjunction of two clauses and computed the projection rule. And it is known that there is a short proof of polynomial of pigeonhole principle. Okay, and open question whether this proof system simulates cutting planes with unary coefficients. Why with unary? Because OBDD has short representation of equalities with unary coefficient, not necessarily in arbitrary case. Okay, the proof system OBDD and the weakening, because this is just a semantic proof system, and since OBDD can represent linear equations, then it's trivial that this proof system simulates cutting planes with unit coefficients. It turns out that there are short proof of click coloring principle in this proof system, and it was even noted by Tseres, Klatis, and Vardia that there is such order of variables such that if we consider refutation where used on all OBDDs use this particular order, then any proof of click coloring has exponential size. So we have one easier order where there is polynomial, and we have another order that it's hard. And this hard order was used by Krajcik to prove lower bound for all orders. The idea was the following: he devised a transformation. Assume that phi is a formula that hard for one particular order pi. Krajcik devised a transformation that whereas sketchy likes as follows. He added variables that encodes a permutation of variables. And part of the formula says that sigma encodes the permutation, and after it we add the formula phi with variables permuted by sigma. And since assume that this formula has short refutation in some order, but we know that there is a hard order, and we substitute this hard order to sigma, and that's why we get a refutation of phi in hard order, and hence it should be exponential size. Very nice extension of this approach was proposed by Segerlind. Segerlind also defines transformation with the same property, but it has some additional important properties. First of all, Segerlind consider a refutation of initial formula, just any variables substituted by or of many other variables. And he considered, since we make this refutation, it is possible to consider not all permutation, but only some small number of permutation from the set of two independent permutations. And using this nice property, it is possible to separate this proof system from other. For example, Segerlind proved that this proof system does not simulate res of log m. And using these two orders, that in one order click coloring is simple, in other order click coloring is hard, it's possible to prove that adding reordering make proof system harder, stronger, not harder. We just consider Segerlind transformation applied to click coloring, and it will be hard here, but since we have a small number of permutations here, we can just we can just use the simple order, always reorder this part for simple order, and finally we have short. Yes.
So just to understand, the second and third result, both of them are fixed orders, but in the second result, it's a different ordering. Or do you allow any?
One order for all.
Yeah.
Here one, or here also one order for all OBDDs. But here, yes, when we apply S to it, we can use.
Okay.
7.
Sorry. No.
Yes.
Krajcik formula. This is hard. Also, if you have a reordering or not? Ah, it's okay.
Well, it's rather complicated to analyze. Well, I think that it's not open. Nobody tries.
Does the lower bound for click coloring go through feasible interpolation?
Now, bound for click coloring here, yes, it's for feasible interpolation. It's used that the OBDDs have small communication complexity if their partitioning business is there. Okay. And this is the whole picture. What we know, and here one proof system simulates other if there is a path with bold, and if not, there is no path, that there is no simulation, and if there is a path that use dotted edge, then the existence of simulation is open question. For example, it is interesting that star does not simulate just if we have only conjunction rule. And also weakening rule can simulate reordering rule. Okay. It's also can be shown that it is in P-hard to automate proof OBDD with and weakening. There is the following theorem that there is a polynomial time function mapping CNF to CNFs with the following property. If phi is satisfiable formula, then the result of this function has a short resolution refutation, and if phi is unsatisfiable formula, then any OBDD and weakening refutation has exponential size. No, the proof strategy, the corollary that it is in P-hard to automatize, the proof strategy is more or less standard and follows Ceres-Müller paper. And first of all, we prove this transformation for one particular variable order, and after it we apply Sutherland transformation. And how to prove for particular, this is similar to automatability of cutting planes. By this paper, this is proved by lifting from resolution block widths to DAG-like communication protocols with many participants, but not too many as was in case of cutting planes in the number in the hand model. But I think that I have no time to speak about it. Okay, and what about where I speak only about OBDDs? What about advanced branching program? Okay, of course, if you consider semantic refutation of advanced branching program, this will be harder. This will be stronger than this proof system, and for this proof system, we don't know any lower bound. This proof system is no, it's a semantics. This proof system is not trivial. For example, it has short refutation for formula based on bipartite graphs. For example, pigeonhole principle, taking formulas on bipartite graphs, and so on. Just the short refutation, we first of all consider end of all conditions for one part of the graph, and it has small OBDD representation for convenient order, and then for the second part in the another order, and just one end, and we will get a contradiction. But it is possible to prove exponential lower bound. And the hard formulas are perfect matching formulas that the following the variables corresponds to edges, and we put down the condition that every vertex is covered and that every vertex is covered twice. And the following theorem holds that if G is GraphG is good enough expander, then perfect matching and setting based on GraphG require such proof of exponential size. The proof idea is the following. For perfect matching, we consider only clauses of this size, the main clauses, and we can find the first moment when we download the quite many of such clauses, and it is not important for us how many such clauses we have. It is possible to show that in this, all such functions has large read-once branching program representation. Actually, this proof holds not only for read-once branching program, but also for non-deterministic read-once branching program. In non-deterministic branching program, such vertices can be marked by or instead of variable. It means that we can go to either direction, and we accept if there is path to one thing. And it is interesting that for this proof system, extension rule can't help. Because all extension variables we can change to this or not. If we consider lower bound, and we can also always can end several extensions such that the resulting formula will be easy to tree-like resolution. And the corollary that even if we consider read-once non-deterministic branch program with end, this proof system will not simulate tree-like resolution. Also, this result implies the exponential lower bound if we admit small number of projection, linear but small. Question?
Just for the beginning of the slide, you said that I didn't understand because you said you have short refutations for citing formulas, but then you said you require
on bipartite graphs.
Okay, so
yes, strong expanders can be bipartite.
Okay, so non-bipartite expander.
Yes. Algebraic expander will spectral expanders are not. Okay, and in that I will say some words about OBDD-based algorithms. The goal is to just solve satisfiability problem and consider the following algorithm that has OBDDD in some order. Initially, it's constant one. It can download clauses from formula, and when it downloads clause, it deletes from the formula. And it also can apply projection rule. If variable x does not appear in the formula, it was also deleted, then we can apply projection rule. And also we add reordering rule that we can reorder our OBDD to any order what we like. And finally, when all clauses are downloaded, we just report whether OBDD we have is satisfiable or not. And running time of this is polynomially connected with the size of the largest OBDD that we have during the execution. And this algorithm was first defined by Ben-Gurion and Vardy. It is known that Itsykson formulas are easy for such kind of algorithms. No, this is not one algorithm where we can apply rules in using different strategy. Also, pigeonhole principle. And if we not use reordering rule, then lower bound implies from lower bound from OBDD proof system. But what if we can use reordering rule? It's even possible to prove lower bound for the case when we have read-once non-deterministic branch program instead of OBDDs. And how this lower bound works? First of all, we prove lower bound for satisfiable formulas, and they look as follows. We consider special linear code, and the hard formula encodes that X is a code word. And but this is satisfiable formula. And how to construct hard unsatisfiable formula. The weak points of this algorithm that to apply when it applies projection rule, it should download all clauses that contains variables. Maybe it's too many clauses. And hard formulas use the following idea. There is trade-off. Either we do not use projection rule at all, or we have to solve hard formula for this proof system. And this also implies this hard example that such algorithms do not simulate tree-like resolution. And my student proof, no, this holds for this proof system, but the formula is very artificial, and my student proved lower bound for formula with clear meaning for bit pigeonhole principle. But here we have OBDDs instead. Okay, and several open questions. First of all, for me, I think it's interesting to prove lower bound here for some natural formulas, and the natural candidate is binary pigeonhole principle. Also, it is interesting to separate weakening rule and projection rule. No, the main question is prove lower bound for this, or more interesting for just for semantic calculus of advanced branching program. There are several questions. Consider a very simple proof system. OBDD with just AND is very simple, but many things not understandable for it. First of all, is it true that bounded Frege can simulate this proof system, or resolution can quasi-polynomially simulate it? To separate DEG-like and tree-like version, to prove that it is open for this proof system that random formulas are hard. It can also be interesting to prove polynomial bound if we just AND, but here two BBs, and it's also open whether this simple proof system is automatable or not. Okay, thank you for your attention. Sorry.
Thank you. You had some questions, and do we have some questions for Dmitry?
So since I have not had this long paper about lot of proof systems with branching program.
I should not consider another model. There was no branch forms are not proof lines. It's something like IPS, but instead of polynomial, you consider branching program.
You have this slide where you mentioned the lower bound on resolution and then OBDDs, and you went very quickly, and I wasn't able to get what you said. That you cannot automatize resolutions. OBDDs.
This is the one. Yes.
So, what does it mean that does it mean that you cannot automatize resolution using? Okay. Yeah.
Yes, the upper bound is resolution and the lower bound is OBDD. So you cannot
automatize OBDD and OBDD. But does it also mean that you cannot automatize resolution using OBDD? Automatize. Yes.
I have a question. So back in the 90s, when people were doing a lot of model checking and so on with OBDDs before SAT solvers kind of came in, one of the things they would do was partition OBDDs and talk about the representation of was rather than a single monolithic OBDD was as a conjunction of some number of OBDDs. How does that, is it possible to compare that with these models?
No, as correctly, most full lies here.
Oh, okay, it does actually like that. Okay. Questions? Oh, okay, yeah.
There is this model that I can not even define it out of my head. It is DNNF. That's who answers. DNNF.
There are different numbers of Ds. There's one with 2 Ds, one with 1 D.
Okay, that's oh yeah, but one is a small capsule.
One has, the first
Okay,
is,
but okay, that's
No, there is some paper with lower bound with this conjunction. So but the proof is almost the same. That's probably
so that but they're probably stronger than OBDD, but are they related with one branching program?
yes, they are stronger than the one branching program, but in that paper they considered something instead of order in that model there is a tree.
right, yeah, so there are different versions of these. There's the decision version, which is like a one BP, except you have conjunction nodes. That's one version. And then there's structured DNF where you've got a V tree or something like that. And so generalization of OBDs that way. And their sentential decision diagrams are some special cases of those as well.
Saying like if this like there are several open problems in OBDD in this regard will be even more difficult, I guess.
Other question? Okay, let's thank Dmitry.